All right. Now, we want to become familiar with what we call a heating curve. And in this heating curve, we're just adding heat to a system of a given material, element, or compound. And we're monitoring how the temperature changes. In other words, when we add heat to a system, what is that heat doing to that system? Okay? And this is the kind of curve that we see whenever we add heat to systems. And it's because of what the heat is doing. And the temperature curve helps us, or the heating curve helps us kind of reminds us of what what heat does when we add it to a system. All right. But if I take a solid, for example, piece of ice, here it is, H2O, solid, there it is, piece of ice. And then I begin to heat that piece of ice. Here is my flame that I'm going to heat the piece of ice with, okay? Let's say the ice starts off at negative 50 degrees Celsius. The ice is really cold, negative 50 degrees Celsius. As I heat the ice, the temperature of the ice is going to increase. The temperature of the ice is going to change from negative 50, and if I monitor temperature as I add heat, right, the temperature will change until it gets hot enough that the motion of the molecules, and that's what we're doing when we're heating it, we're making the molecules move. The motion of the molecules is such that the molecules will begin to receive enough energy to actually transition into a liquid phase. So we'll heat up from negative 50 up to 0 degrees Celsius. And once we reach 0 degrees Celsius, the heat will continue to be added, but the heat will no longer increase the temperature of the water. It will continue to move the water, make it move faster and faster, but the energy will not be invested in actually increasing the motion of the solid. Within a solid, it will be moving the solid into a liquid phase, right? And so the solid water will be transitioning into a liquid phase, and all the energy that's added will be absorbed by this system, and the system will not increase in temperature, it will just melt. So here we have a melting curve where we've heated it and now we're melting the water, or the ice, into liquid. Now let's say this is all contained in a vessel, and we move on. Now I'll cover this up. Now we're all melted, and our vessel now just contains liquid water. I still have my flame heating my water, right? And the water now, once it has all been converted to water, it'll be initially 0 degrees Celsius, but the water will begin to heat. And the water will go from 0 and it will change temperature. And it'll continue to change temperature until it reaches a certain point. And if this is at 1 atmosphere of pressure, what temperature will it reach? Let's see. Oh, look, it's Sarah's turn again. Sarah, what temperature will it reach before it begins to flatten out again?
Is it 100 degrees Celsius?
That's right. When it gets to 100 degrees Celsius, then the energy, the heat from the heat source, will no longer go into raising the temperature of the water, but it'll go into what, Sarah?
Into making the molecules move?
Making the molecules move from what? Where are they going to transition now?
They will move into
This was a transition from a solid to a liquid, melting, right? So what are they going to start to do here?
So they will transition into a gas.
That's right. A liquid to a gas, that's called what?
Evaporation.
Evaporation. Good job. So, all of the heat will be absorbed by the molecules as they leave, going from solid or liquid to a gas. Okay? After you get them into the gaseous phase, right? After you get them all into the gaseous phase, then you could continue to heat that gas, and that gas's temperature would increase. If you want to contain the gas, you'd have to, have some sort of a container, otherwise it'll just all fly away and condense somewhere else. But that's what we're looking at when we look at these heating curves. We're looking at the solid heating and then all of the heat going into the transition of that solid to a liquid, the resulting liquid heating, and then all of that liquid transitioning into a gaseous phase. And then that gas can continue to be heated, get hotter and hotter and hotter. Okay? Transitions going the opposite direction, where we remove heat, right, will follow the same trend. Now again, as we go from, for example, liquid to gas here, right, that process requires energy. To go from a liquid to gas, it removes energy from the surroundings. It requires energy. Same thing going from solid to liquid, it requires energy. And why does it require energy? Well, maybe I'll let somebody give me an answer for that. Landon, what do you think? Why does it require energy to go from solid to liquid?
The energy is needed to overcome the state of which it's at, and the only way that can happen is overcoming the intermolecular forces.
That's right. So the energy required to go from solid to liquid or liquid to gas is the energy to overcome those intermolecular forces. Okay? So, we used to do problems where you would tell me, for example, how much energy was required to heat 1 gram of water from 0 to 5 degrees Celsius. Remember that? We used to answer those kinds of questions. How much energy is required to heat an amount of water, a certain mass of water, from this temperature to a different temperature? And we could answer those questions fine. Now we're going to have questions that require a little more thinking, like this one, where it says how much heat is required to convert 10 grams of ice from negative 10 degrees Celsius to water at 50 degrees Celsius. Okay? Now this is a little bit different, right? This is a little bit different. All the questions we had before about changing how much energy was required to change the temperature of a substance, all of those questions never encompassed an actual phase change, right? If I wanted to know how much energy, like this, how much heat in joules is required to convert 10 grams of ice, if instead of starting at 10 degrees Celsius, well, I just went from 0 to 50 or 0 to 60, because here we can see the change is negative 10 to 50. That's 60 degrees. So could I just answer this question by saying how much heat in joules is required to convert the 10 grams from 0 to 60 degrees Celsius? If I wanted to answer that question, go from 0 degrees Celsius to 60 degrees Celsius, right? What would my change in temperature be, Leata? What would my change in temperature be, Leata? Taiwan, what would my change in temperature be? If I'm going from 0 to 60 degrees Celsius, what's my change in temperature? Very good, 60 degrees Celsius. And Taiwan, what else would I need to know to know how many joules of energy are necessary. I say Q is going to be equal to, what else do I need to know?
Mass.
That's right, I need to know the mass, how much water. What else do I need to know? The specific heat of the material that I'm heating. How much energy does it take to raise 1 gram of that material 1 degree Celsius? And then this is where I put my change in temperature, which is my 60 degrees Celsius. So if this was water, do you remember the specific heat for water, Taewon?
It says on the graph, right?
Yeah.
4.1.
4.184. And that's joules for every gram degrees Celsius, right? So let's move this out of the way really quick. Get a little closer here. Whoop. So 4.184 joules for every gram degrees Celsius, and I know I'm going to change it 60 degrees Celsius. How many grams am I talking about here, Taewon? Whoops. How many grams am I talking about? 10 grams. Very good, 10 grams. My microphone is falling, or my camera's falling apart. Let me fix it there. Okay, 10 grams. So, to solve for joules, I can just take 10, multiply by 4.184, and multiply by 60. And that would tell me how much heat is required to raise 10 grams of water 60 degrees Celsius. That's a little review. But in this problem, we're not doing that exactly. We're going from -10 to 50. And so for 10 of those degrees, we're not heating water. For 10 of those degrees, we're heating what, Jace?
Ice.
Yeah, we're heating the ice. As we go from -10 to 0 degrees Celsius, we're heating the ice. And then as we transition from 0 degrees Celsius to 1 degree Celsius, what happens in between there, Brielle?
Hit the question one more time.
When we transition from 0 degrees Celsius to 1 degree Celsius, something special happens to the ice. What happens?
It's melting.
It's melting. It's melting. And so there's some energy associated with that, and that's called the enthalpy of fusion. The enthalpy, energy, heat energy, associated with the fusion of a compound. Okay? So, to solve this problem, we need to, just like before, where we would set up a problem like this, where we'd say the amount of heat required is associated with the mass of material, the specific heat of the material, and the change in temperature of the material. But we're going to be doing that for kind of like two materials, because we go from -10 to 0. This is as ice, right? And then we go from 0 to 50 degrees Celsius as water, liquid, right? And in the transition here, we have the delta H of fusion that we have to add to the total energy as well. Okay? So Harry, how much energy does it require to go from -10 degrees Celsius to 0 degrees Celsius for a piece of ice? Not just any old piece, 10 grams of that ice. What do you think, Harry? How much energy?
Are we using the formula that we just covered earlier?
Yep, it's going to be the same formula. Q equals ms delta T. What's our delta T, Harry?
10.
10, because we're only going from -10 to 0. What's our specific heat?
1.8.
What's that?
2.18.
2.108, is that what you said?
Oh, yeah. Oops.
Yeah.
Yeah, that's what I meant.
2.108, that's how many joules per gram degrees Celsius. And you chose that one because we're heating ice, right? It's different for liquid water, but we're heating ice. And then mass, what's there, Harry?
So 10 grams.
10. All right, so we got 2.108 times 100. That looks like 210.8 joules. Is that right?
Yeah, that's what I got.
So that's how much energy is necessary to heat the ice from -10 to 0. Now, Sarah, could you help us with the portion of going from 0 to 50? How would the equation look for that portion, Sarah?
All right, so I think you would use this specific heat of water, which is 4.184,
That's right.
and then the change in temperature is 50 degrees Celsius.
That's right. 0 to
I
50.
believe.
Mm-hmm.
And 10 grams.
10
If
grams.
it- Yes.
Still 10 grams. Very good. So, any calculators out there? 10 times 4.184 times 50?
2,092.
Excellent. 2,092 joules of energy. Okay? Now, Landon, should the sum of these be the answer to our question? Is it up there?
Yeah, I got 2,302.8, and I see 2,304.
So you added these together? Is that what you did?
Yeah.
All right. Now, is there any reason that there should be more energy associated with it?
I think the enthalpy of fusion should be included, but I don't know exactly where that would fit.
Okay. And that's exactly where you're going to find yourself on the exam. You're going to be like, I know how to do this. This is stuff that we did before with the water. We never went transitioned, and so this is kind of new, this top part here. Right? But I know, because we did discuss it, we know that there is some more energy that has to overcome the intermolecular forces for that melting. But I can't remember how this information helps me. Well, maybe if we stare at the units long enough. What is it telling us here? What are the units telling us, Landon?
That it's kilojoules over moles.
Kilojoules, yeah?
Yeah, is that just energy over moles?
Yeah. What would that mean? What does it mean? 6.010 kilojoules per mole to do what to that mole of what? What's it talking about?
Per mole to change.
That's right. To change from what to what?
Change its state from solid to liquid.
Solid to liquid. We knew it was solid to liquid because it says fusion. Fusion. The enthalpy of evaporation will be a different amount of energy for every mole of material. Okay? So, we looked here and it says that much energy for every mole of the material. Fusion, it tells us the delta H is the energy for that much material to melt. Okay, now, do we have a mole of material, Landon?
I think so.
How many grams of water do we have?
We have 10 grams.
10 grams. How many grams are in a mole of water?
10 grams are in a mole. Oh, isn't it 18?
18. That's right, 18 grams a mole. So we don't quite have a mole, do we? But we can solve for joules, the amount of heat energy. They provide it in kilojoules up here. But we have our answers over here in joules, and we want to add on. This is the heat necessary to change the ice from -10 to 0. This is the heat necessary to change the water from 10 to 50. We want to add on the heat necessary to melt that block of ice. And so we want to put it in joules because these are also in joules, right? So we'll want our answer in joules. All right. And we know we have 10 grams of water, but I need to know how much joules it takes. 10 grams of water, but it's solid water, so it's ice. I want to know how much energy it requires to melt that 10 grams of water. I can go from grams of water to what? What can I transition to? There, Leata, do you see it? Leata, I don't know if has been around today. Taiwan, do you see it? What conversion factor can I use to transition? Oh, Leata's here, good. What conversion factor can I transition from grams of water to energy with? You see this here? It says 6.010, right?
Yeah.
Kilojoules for every mole of what, Leata?
Mole of water.
Water. So maybe I should go from grams to moles of water, right? Because then I can go from moles to what? Kilojoules of heat, right? And then kilojoules to joules. 1,000 joules for every 1 kilojoule. Okay? So how many grams in a mole of water, Leata? $18, very good. 18 grams for every mole. And then, what's this relationship here? Moles of water to kilojoules of energy. Where do I get that?
The 2.108.
That,
6.
yeah, very good. 6.010 kilojoules for every mole of water. And then I threw in here the 1,000 joules to get to kilojoule of energy. Great. Can somebody give me an answer for this? How many joules of energy is this going to take to melt my 10 grams of ice? Somebody type a number in the chat box for me.
I got 3,338.9.
Second witness, anybody? I'll let you guys do it. Sarah got it as well. Excellent. So we have in here 3,338.9 joules of energy. And now we can search for our answer because we have this energy here. What was this energy, Taiwan?
Energy from ice to water.
Well, it's energy heating the ice from a -10 to 0. Very good. And Jace, what was this energy?
Heating it from the water to 0 degrees to 50 degrees.
Very good. And this water, this one here, Brielle, what was this energy?
Going from ice to water is the entropy fusion.
Very good. So the sum of those three should be our answer. Is that up here anywhere? Looking like about A or B?
Yeah, B.
B. Excellent. Very good. So now we can answer these kinds of problems. Not just ones where it says how much energy is required to heat this water from 20 degrees to 80 degrees. Fine question, fine question. But now we can actually answer the question, how much energy does it take to heat this water from -12 up to a +18, for example, right? Because we're heating ice for a section, we're melting it, and then we're continuing to heat the water up to a higher temperature. Excellent, very good. All right, let's try to look at, well, I think this is a good place to stop. Next time we'll talk about our phase diagrams, but for now, I think this is a good place to stop. If anybody has any questions, you're free to hang around or ask them. Otherwise, I will see you guys on Wednesday. And let's see, are we going to be able to finish this chapter by Wednesday? We'll probably finish it on Wednesday. And so we can imagine maybe an exam opening on maybe Thursday or Friday, open till maybe Thursday of next week. Okay? And it'll be just an online exam. That's an estimate right now. I'll know for sure at the end of next class when we open and when we close. But